again. So I've got my uniform electric field. So I've got a uniform electric field. And we just did a problem just like if we were dealing with the Earth system. So here's my Earth system, and I have my mass, and it's going to be directed towards gravity, and it's going to go down. We just did our velocity final is equal to our velocity initial plus my acceleration times time, just like we did in General Physics 1. And we got this going here. Now, one of the things is that force is a vector, velocity is a vector, my electric field is a vector, and we've got all of these things that are vector quantities. Which means they have direction and magnitude. Now, one of the things that when we were in General Physics 1, we talked about how we could do this same problem, and we didn't necessarily have to do this idea of my vector quantities here, because we had our concept of work. And work, just to remind everybody, the definition of energy. So we have our definition of energy, which is my favorite definition of all of physics. My definition of energy is the ability to do work. And we talked about potential energy. And that was looking at, if I was dealing with potential energy associated with gravity, we talked about the fact that here's my ground level, and I actually have to do physical work to raise my object. My object has weight, which is my force. And then we had to deal with a height, X or Y, depending on which way we were dealing with that. And we had this idea that work, my value of work, was going to be the dot product of force times distance. And we talked about that in that this gets us our dot product, but our biggest bang for our buck is when our cosine is equal to 1. And the magnitude of the work was going to equal mgh for my potential energy, or we could write that as mgx. So we did all of that derivation back in General Physics 1, but we dealt with the fact that we were dealing with this, but we ended up with this dot product, which got rid of our vector notation. So energy was a state function. It didn't matter where I was or how I was getting there. It didn't matter. We didn't matter at all. So we could look at, which kind of interesting is if I'm looking at this system here, we can look at potential energy. If this were a positive charge, right? If that's a positive charge, and I have a positive or a negative test charge there, my potential energy is going to look like Q, this right here, over R. So we end up with this over R, and that's a potential energy function that we have. And we now have had to do work to get us there. So that's kind of an interesting twist on our system. So if I put in an object, so let's go ahead and let's say that this is a negative charge. Because remember, this is the positive side and this is the negative side. I'm going to have to do physical work to move this object from here to there. I've got to do work. And in this case, what's going to happen is our work is going to equal our change in potential energy. And in this case, we've got our change in potential energy is going to be related to, and we're going to deal with the magnitude here. This is my electric field. Okay, that's all right. My electric field times my distance. And we end up with a negative here, all right? End up with a negative that we've got because we're going to this part. And so we can define electric potential we're going to define electric potential as a V. And this is where life gets kind of entertaining. Our electric potential is going to be a volt. All right. It's going to be a volt. And we can define that as our KQ over R. And that's coming back from my change in work in my field. So we get that, and basically we get our forces and we can come in and play. And so you can go back and you can look at how that all works. Now, what's nice about that is now I've gotten rid of my vector character. Gotten rid of my vector character. I can look at my change in energy and we can actually do some problems. So let's do a problem. So I'm going to have a device. I've got a plate that's a positive plate. I have a negative plate. We're going to, in this case, we're going to use a proton. So this is a positive charge. We're going to move it a distance. Okay. And we've got the mass of a proton is 1.67 times 10 to the minus 27 kilograms. We've got the charge on my proton is 1.602 times 10 to the minus 19 coulombs. We're going to call this point A, and we're going to call this point B. The velocity at point A, this is velocity, so it's a little v, is 75,000 meters per second. The velocity B is equal to 93,000 meters per second. We want to know what is the potential. So this is a little different than what we've done before. But remember, if I'm dealing with energy, I can look at my change in kinetic energy. And that's just 1/2 mv squared. And I'm looking at that change in that. So I'm going to do my 1/2 m, and I'm going to do my 93,000 squared minus my 75,000 squared. And if I plug in my numbers, I'm going to end up with 2.5 times 10 to the minus 18 joules. Because remember, we're in energy, so I've got to be in joules, and that's out there. And now that joules is where we're at, and now my electric potential, and this is my electric potential, is going to equal my change in energy divided by my charge. And now I'm going to get my 2.5 times 10 to the minus 18 joules divided by the charge on my proton. 1.6 times 10 to the minus 619 coulombs. And look at this, I got joules, coulombs, and a joule coulomb is equal to a volt. Just so you know. And this gives me 1.6 joule coulombs or 1.6 volts. Now, this is one of those things of now we have to decide what's the direction. This is what's going to be different in our electrical systems than in our other systems. But in this case, we've got it moving in the same direction. So we're going to move from there and we're going to end up with a negative 1.6 volts. I encourage you to go and play with your scenarios on that lab so that you can actually see this kind of a thing. But once we voltage, if we know the voltage, we can find our electric field, which is really cool. So my change in voltage, my voltage V is going to equal off ED. So I've got voltage divided by D. And if we know our distance, but if we know the distance, and in this case, my distance is 0.1 meters, this will give us a negative 1.6 volts divided by my 0.1 meters. And that gives me 16 voltmeters. And this voltmeters is another unit for electric field. So if I've got a joule coulomb, and then we have Newton coulombs, okay? This is what we were working with yesterday. And now I've got joule coulombs as a volt. So I'm going to end up with a joule coulomb, and I want to show that that's a voltmeter. I want to show it's the same as a Newton coulomb. So there's my voltmeter is equal to a joule coulomb meter, which is equal to a Newton meter divided by coulomb meter, which gives me a Newton coulomb. So we can show that our units are the same. So a couple of points I want to make. One is for my electric field, we get K Q over R squared. All right, that's my electric field. And for my voltage is going to be go back to where we had that before. K Q over R. So my voltage as I move away from a charged surface is going to go away as 1 over. So for those of you that are dealing with the MCAT or something like that, this idea here of it where I'm dealing with my R and my R squared is a good thing to remember when you're going in for your MCAT or doing something along those lines. Okay. Getting ready to do some more problems here, but this is why working with potential is so much better. Can anybody hear me or did I lose people?